All right, so let's work this problem. So we've got a cantilever beam with a load of 5 kips in the middle. Before we do this, let's just talk about what you'd have to do if you wanted to do direct integration. So for direct integration, could you write a single moment expression that was valid for the whole structure? Not really. You'd have to write one good for the first 15 feet and then a second one. And of course, each of those would generate 2 integration constants. So you'd have to do some kind of matching at the middle. I mean, you can do it. It would not be terribly hard. But remember, all this problem wants is the slope and displacement at the free end. So you do all that work and then you just evaluate your equation at B. So as an example of a different way to do it, let's try conjugate beam. So the first thing we have to do in conjugate beam is build the what? Well, we got to have the moment. So let's draw the shear and moment diagram for this structure. So just to get started, I'll come over there at A, and I will assume I have a positive shear at A and a positive bending moment at A. And I'm going to have to find those values, right, to get started. So what's going to be the easiest way to find the bending moment at A? I would sum moments at A. So I'll come over here, and using right-hand rule for my sign convention, I will sum moments at A and make sure everything's in equilibrium. So with right-hand rule, this moment is actually a negative moment. And this 5 kip force about A also creates a negative moment. So the force would be 5 kips, and the distance would be 15 feet. So it looks like my moment at A is negative 75 kip feet. So I have a negative bending moment at A. Does that make sense?
Yes.
Yeah. So while we're thinking about that, I'm going to go ahead and draw what I think the deflected shape might look like. Something like that. Now, how do I know that? Well, I know at A the displacement is 0 and the slope is 0. So as it curves out, probably my maximum displacement will be at B, and my maximum slope will be at B. And what kind of slope will I have there? Is that positive or negative slope?
Negative.
That's a negative slope. And of course, the displacement is also negative. So I'm hoping those are to be the 2 values that I can find. Also, look at that curve. What kind of moment generates a curve like that? Positive or negative bending moment? Negative. So we're starting off with a negative bending moment. That seems reasonable. So far, so good. Now let's sum forces in the y direction. And what do we have? I've got my shear force acting up. That's positive. I've got my 5 kip force acting down. That's negative. So it looks like the shear at A is 5 kips. So I've got enough now to build my shear force and bending moment diagram. So I'll build a little template quickly. And I'll start off with my shear, and all these values will have units of kips. So what is the shear at A? 5, so we'll start at 5. I probably should have added in this midpoint line. I'll come back and put it in there. And we know that the change in shear between these 2 points is the area of the load, which is 0. So if I start at 5, I won't change. I'll stay 5. I also know the slope of the shear diagram is the load. The load is 0, so here's 0 slope. So there's my shear diagram over the first 15 feet. And now as I go left to right, you can see my shear will change exactly minus 5 kips. So it goes from minus 5 to 0. And then the change in shear from 15 to 30 is the area of the curve, load curve, which is 0, so no change, that's it. So the first half has constant slope of 5 kips, the second half, no slope. No shear. I said slope, I meant shear. So now we'll draw the moment diagram. And this will have units of kip feet. What's the moment at A?
Oh,
No, negative 75. What's the moment at B? 0. So I know where I'm starting and I know where I'm ending. And we know the change in moment between any 2 points is the area of the shear diagram. So this area is positive, has a base of 15 and a height of 5. That's positive 75. So negative 75 plus 75 brings me to 0. And I know the slope of the moment diagram is the value of the shear, and the shear is constant and positive. So there's my moment. And the change in moment from here to here, 15 to 30, should be there in the shear diagram, which is 0, so I'm done. So the second half of the beam also has no moment, like it had no shear. So there's my moment diagram. So I need to add that as load to my conjugate beam. So let's do that. So I'm going to draw that right below here. So here's my conjugate beam. So a fixed connection becomes what in the conjugate space?
Free end.
Free. And a free end becomes fixed. So basically, in this particular idea, my beam just turns around, it looks like. Now again, that's not always the case, but it is the case today. And now what I like to do is I like to just imagine taking that load, that moment diagram, picking it up, boom, and dropping it right on the beam. And when I do that, I get something that looks like this. And that has a value of 75 kip feet. That's the moment. But now in the conjugate space, we divide it by EI. Now, what's the direction of this load? Well, this is what kind of moment? Positive or negative? Negative. Negative load is up or down? Down. So this becomes a negative load. And just to give you the dimensions, don't forget this is 15 and this is 15. So there's our conjugate beam. Now that we have the conjugate beam, what was the question? The question was, what is the slope and displacement at B? Slope and displacement at B is shear and moment at B in the conjugate space. So if I come back down here and imagine positive shear at B and positive bending moment at B, if I can find those two things in the conjugate beam, then I will have found the slope at B in the real beam, and the moment maps to the displacement. So looking at that problem, that's not a very challenging problem. Just basically finding the reactions. So how do we do that? Well, I can sum moments here and get to B, and I can sum forces. So the first thing I'll probably want to do is turn this into a concentrated equivalent force. So I'll just draw it in. I'll just call that F. And then I'll want the distance from the support to F. I'll call that D. So what is F? What is the area under this curve? It's a triangle, so it should be 1/2 the base, which is 15 feet, times the height, which is 75 kip feet, divided by EI. And what does that equal? That's not one I can do in my head. Anybody have a calculator? What's 7.5 times 7.775? 525, I'm guessing.
562.
Oh, that's close. 562.5?
Yes, sir.
And that will be kip feet squared over EI. And then what would be D? Well, from here to here is 15. And then from here to the centroid is what? Well, how far is this fit right here? It should be 2/3 of the bottom. 2/3 of the bottom is 10. So it should be 15 plus 10. Right? So it should be 25. You guys see that? See, from here to here is 15. And from here to here, that's 2/3 of the base, which is 15. So that 2/3 of 15 is 10. So that's 10 feet. 10 plus 15 is 25.
Would not be 2/3 of 30 feet?
No. It's only 2/3 of the base of the triangle.
Okay.
So now to find the moment, I would just sum moments at B. And what do I get? Well, I have my moment that I assumed, and with right-hand rule, that's a positive moment. And then I've got the moment created by this force F. What kind of moment does that create about B? Positive or negative? Positive. So it'll be plus the force, which is 562.5 kip feet squared over EI, times the distance, which we computed as 25 feet. And that's it. So then the moment will be negative whatever 525.5 times 25 is. 14,062. I remember that. Is it 14,062?
0.5.
Okay. So 14,062.5, and that's going to be kip feet cubed over EI. Now, we can check a few things. First, it's negative. So remember, moment in the conjugate beam maps what back to the real beam? Displacement. And is the displacement at B positive or negative? Negative. So that sign seems to be okay. It's not unusual that the numerator is a relatively large number because remember, we're going to divide by E and I. And for steel, in kips per square inch, E is 30,000. So that's already 14,000 divided by 30,000. That's less than half an inch. And then you're going to divide it again by 800. A lot of the problems, you just stop here. Like if I don't give you a value for E and I, you're done. Right? If I do give you a numerical value for E and I, you have one more step to do. So you take your 14,062.5 kip feet cubed, and you got to divide by a few things. First, you divide by 30,000, and that's kips per inch squared. And then you divide by 800 inches to the fourth. And then you need to convert. So I like to convert cubic feet to cubic inches. So I've got 1728 cubic inches in a cubic foot. And let's see, so kip cancels kip, cubic feet cancel cubic feet. I've got inches to the fifth in the numerator, inches to the fourth in the denominator. That's just inches. So what does that come out to when you compute it?
1.01.
Yeah. So basically about an inch. This end dropped an inch. Wow. That's a 30-foot beam, which is about the length of this room. And I put 5,000 pounds in the middle of it, and the end only deflected an inch. But 800 inches to the fourth, that's a fairly stout beam. Okay? Let's just say your chipboard beams will not have a moment of inertia of 800 inches to that fourth. Now, if my boss told me, oh yeah, the code says we could go up to 2 inches on the end. So then how can I save some money? I don't need 800 inches to the fourth. I only need 400. So I can go find a lighter, cheaper beam to do the job. So when you're a structural engineer, many times you know it can handle the load and the stress. You know it can handle the displacement, but you may be making choices to lighten the structure. And of course, that saves money. There's a whole area of research called structural optimization, where most people, that's all they're interested in. They're trying to meet all the codes and all the criteria and do it for as little money as possible. All right, we got one more thing to do. We need to sum forces in the y direction. I know I'm a little bit late, but hang in there. So my shear force is down, shear at B, and my load is down, and my load was 562.5, and that was kip feet squared over EI. So that's pretty easy to solve. It looks like the shear at B is negative 562.5 kip feet squared divided by EI. Okay, so qualitatively we see it's a negative value. Remember, shear in the conjugate beam is slope. In the real beam, we already suggested we think that the slope is negative. It looks like we've got that part right. So let's see what the actual value is. So if I can compute the value, I've got negative 562.5, and that's kip feet squared. Now I've got to divide by E and I. E is still 30,000 kips per square inch. I is still 800 inches to the fourth. But now I've got feet squared. So 12 squared is 144. So I'm going to have 144 square inches in a square foot. And if you look at all those units, they cancel out. Kips cancel kips. Square feet cancel square feet, and I got inches to the fourth at the top and inches to the fourth in the numerator. So what's that number? It's probably going to be very small. 0007. I just like to say 007. That's not right.
Well, to the negative.
Oh, so what's it going to be? 0.003 something? That's close enough. And that'll be in radians. Rads.
So if we assume the different sign convention for shear, is that okay?
No, you can't do that. Shear has a sign convention. You got to use it. You can't choose a different one. Shear is shear. Force is whatever. Well, force is not whatever. Force, you get two choices, up or down. Right? Same thing with moment. Right-hand rule, clockwise, counterclockwise. But with bending moment, you don't get a choice.
On your conjugate beams, why don't you bring down the 5 kip force in the middle?
Plus, the conjugate beam is only applied with the moment diagram.
Okay.
And this is the moment diagram that reflects that 5 kip force.
Okay.
It's almost like two problems in one. Now, I'll let you go in just a second. The danger is, if you mess up the moment diagram, you're kaput, using the German term. Das kaput. Okay, so I think what I'll do is, since we just got started with these, I think for homework I may give you another direct integration problem, maybe one that's a little more challenging, and then try to find two like little baby versions of this, like simple ones, like maybe ones that look very similar to this. Okay? So have a great E-Day. Be kind to your younger selves. Unless they deserve a stern look, then give it to them. Let's see it. Oh, I had some homework. Some of you guys came in late.
Yeah.
Oops. Mr. Jackson, was Mr. Jackson? He's here. Oh, he's not here. Is he still here?
I only barely know most people's first names at this point.
Okay. Dr. Campbell, real quick. You you've got the shear force draw on the outside in the fixed connection, but technically it would be right there at the beginning of the beam, correct?
That's what my question was. Is it like that? It wouldn't go positive shear. It's only inside if you cut it, right? You get a 93.
Down on the right side.
No, I'm saying that that's what we got down there.
It makes the beam
Oh, that's what we got on part of the
yeah, rotate clockwise another way. Okay. What's not to see?
Well, I mean, I know what you're saying, but I don't.
What there? Got it. Where's positive shear?
Yeah, I understand that, but I mean, your negative sign. I need to work with it. I mean, I understand.
I don't do any negative anything. I just do this.
I know, but it's.
Then when I compute it, it comes out to be negative. That's just the way it is. If I had a different loading, it would come out a different sign. Right?
Yeah.
Same thing when you did that beam. I assumed it was up. It just happened to come out positive. I assumed the moment was positive. What did it come out to be? Negative. It just is.
I know what it is.
And if you look at a beam like that, and how's it going to bend? Yeah. What shape is that?
Negative.
So you should expect the moment to be negative.
I mean, I understand.
There's no new things.
I mean, I understand it. I mean, I understand it.
Can you explain where the rating occurs on the original beam?
The what?
The slope.
It's at B. It would be the slope right there at the very end of B. The slope starts off at 0 and it changes continuously to B, and that would be the largest slope in the construction. It's very small.
You mean to check him?
No, man. You think about a 30-foot beam at the very end, just deflecting an inch. It'd be a pretty small slope. Okay. That's typical. If you get big numbers for the slope, something's going wrong. Remember, 2 pi is a circle. So if you get even something like 45 degrees, that's probably, if any of your beams like that, you have massive displacements. It's probably not right. So if it's under Earth. That's a completely different thing too. But that would just, if you get an earthquake, it would be vibrating. So it's not so much that the ultimate displacement, which can be super damaging. It's the fact that it's going back and forth and vibrating and accelerating. You get a lot of structural damage just from acceleration. Like you would get, if you were in a building that was accelerating a lot, you would have a lot of damage just due to the acceleration. You'd probably fall off your feet, hit your head on something. Well, it happens. Even the best athletes in the world, if they get hit right about here, they just go flying. Some of the most spectacular collisions in football occur when someone's running really fast and someone hits them a little low. They showed this picture of this one receiver who went up to catch a ball and somebody hit him right there and knocked his feet up in the air, and at his highest point he was 10 feet above the ground. Almost horizontal. And then he fell onto his back. And the most important thing was, he got up. I'm pretty sure if I fell from 10 feet, flat onto my back, I would not get up. I would probably be down there for a bit.
That shock alone is enough to just keep you there.
What's that?
The shock alone.
Oh, yeah, you'd knock the air out of you for sure.
Every time.
And who knows what it would do to your head, because I probably wouldn't be wearing a helmet. Oh, you missed a good discussion. Sorry you were out. We're talking about it.